So, welcome to today's class. So, today I'll be discussing the assignment 2. Now, in assignment 2, what we will be discussing is we will be discussing the which was left in the last class. Someone pointed it out, the motoring and generating action of single conductor. Okay. So before going to the motoring and generating action, what we need to do is we need to see these two fundamental rules, Fleming's left hand rule and Fleming's right hand rule. In the last class, we have also seen the right hand thumb rule for finding out the if there is a current in the solenoid, then what will be the kind of flux lines, and if there is current in the straight line, then what will be the kind of flux lines around it. So for that, we use right hand thumb rule. Now today we will be seeing the Fleming's left hand rule and right hand rule before going into the discussion. So you see, so Fleming's right hand rule, so this is, so let me draw this kind of distinction here. So this Fleming's right hand rule is used to find current direction or to find polarity of EMF induced when a conductor is moving in magnetic field. So, what all things we are provided with? We are provided with the magnetic field. Okay. And then we are saying that this conductor is moving. Okay. So, this conductor is moving. So, we have movement, we have magnetic field. And what we get? We get EMF induced. Okay. So this is for finding out this direction of the induced EMF, we use Fleming's right hand rule. So this is applicable for in generators, right? Because in generators, what we do? We give the movement using the prime mover in the presence of the magnetic field, which is generally generated by using the permanent magnet or the some DC coil, current carrying coils. Okay, so this is used to find the this can be extended to find the direction of EMF induced in generators. Now coming to the Fleming's left hand rule. So in Fleming's left hand rule, so let me write, it is used to find direction of movement. Okay. When a current carrying conductor is placed in magnetic field. So let me write this with other color. So I'm writing this with other color. So we find direction of EMF slash current. Okay. So this is to find current direction. Okay, to find current. So here we are finding direction of movement. Okay, when we have a current carrying conductor and when it is placed in magnetic field. So this is applicable for motors because in motors what we have is here also we have in motors also we have current carrying conductor, right? So there is current carrying conductor and there is magnetic field. And what we get is we find direction of motion or force. Okay. So this is important while going into the discussion. Okay. So now let's go to the next slide. Now in the next slide, we will see because in today's assignment there are some questions based on this structure here. So I'll be discussing what this structure is. So here there is a conductor. Okay, so this is the picture which is taken from the professor's lectures. So here he has what he has drawn is he has drawn a current carrying conductor which is placed on the two rails. Now beneath the rail there is one north pole and above the rail there is a south pole. So what will happen is there will be a magnetic field, right, from north to south. So this is the direction of magnetic field from north to south. Now what we are saying is that, so let us write down. Okay, so here what we are saying is that we have placed a, okay, moving conductor, moving conductor in the magnetic field. So we have placed a moving conductor in the magnetic field. Okay. So now again going back, we can see that when we have, so let me just write this. This is moving conductor in the magnetic field. Okay. So we have moving conductor and we have magnetic field. So what we can find? So we can find the direction of EMF induced. Okay. So how it will be? So what we have is, so let me draw. So this is the direction of the magnetic field. This is B. Okay. Now, what about the movement? Movement is like this. So movement is in this direction, V. Okay. So now by using the Fleming's right hand rule, we can find the direction of the EMF induced. So use Fleming's right hand rule. So if you use Fleming's right hand rule, so you place the three fingers in your right hand in perpendicular with your thumb pointing towards the direction of the movement, velocity, your forefinger pointing upwards. Okay, then you will see that your in your the middle finger will come out of the plane. Okay, so it will come out of the plane like so, dot. So generally you will see that, so this dot means what? So here it is like this. So here your thumb is like this, your forefinger is like this. So you will see that your this middle finger will be something like this. Okay. So it will be something like this. So this is the your finger. So this finger is pointing towards the direction of the current. Okay. So the direction of current is here. Now this current is leaving which terminal, whether it is leaving Y terminal or whether it is leaving X terminal. Right. So it is leaving Y terminal. So the terminal which it is leaving, that terminal will be the positive terminal. Okay, because current in a battery also comes out of the positive terminal. So that is why the current, because current is leaving the Y terminal. So that is why current coming out of the Y terminal is taken as the positive terminal. Okay. So current is coming like this. So this is the direction of the EMF induced. So this is Y. This is X. Now coming back to this dot, you will see that this is the, so I have drawn what? I have drawn a dot, right? So what does this dot means? Okay. So generally you will see that in our notation, that something we write with a dot and we write something with a cross. Okay, so what does this mean? So suppose you see an arrow which is coming towards you out of the notebook. So when you're seeing an arrow which is coming out of the notebook, what you will see from the front? You will see from the front the point, right? So this point means it is coming, the arrow is coming out. Okay, because from the front you will see the point. So that is why with the dot we notate that, no, we write the notation that okay, this is the tip of the arrow which is coming out, the front point of the arrow. Now if suppose you see from the back of the arrow, you will see what? You will see a cross, right? Because of this crosshairs at the back, at the arrow, at the back of the arrow, you will see there are some crosshairs, right? That is why this at the back of the arrow, you will see the, if the arrow is going away from you, you will see the back of the arrow. So arrow is going into the plane. Okay. So you will see the cross of the arrow, which is the back side of the arrow. Okay. So that is why this is, so this notation knows that, means that this direction is into the plane, it is going away from you, and this notation means it is coming towards you, the arrow is coming towards you from the plane, so you can see the front tip of the arrow. Okay, so that is what this dot and cross notation means. Okay, you will see that most of the places this dot and cross notations are used. Okay, now, so we have used Fleming's right hand rule to find the direction of the EMF. Now, what about the magnitude of this EMF induced? So we know that from the Faraday's law, what is the EMF? EMF is the rate of change of flux, right? So let us say this V EMF is rate of change of flux. Now, what is flux? Flux is nothing but B into A, which is flux density into area. Now, what is the area? So let us say that this L, so we have to find the area of this conductor with the movement. Okay, so let us say it is moving in this direction by dx distance. Okay, so let us say it is moving in this direction by dx distance. So what will be this area? So this area will be, so this area will be like this. So let me use some other color. Okay. So So this is the dx distance it has moved. So this will be the area. Okay. Because you see flux density is going up like this. So this a portion which I have shaded with the orange color, so this flux density is perpendicular to this, so this area with orange shaded area is perpendicular to the flux density, right? So we generally, whenever area we are taking in this flux density into area, this area means the area which is perpendicular to the direction of the flux lines. Okay, so flux lines are going upwards, whereas this area is horizontal. Okay, so that is why this area I have written like this. So instead of this area, what I will write is, I will write B into L into dx, because this area is nothing but length L. This is because this is the length of the conductor L, and dx is the width of this area, right? So because it, let us say it is moving dx distance, it has moved dx distance due to this move, this velocity. Okay, so what we will get? We will get b L d by dt of x, and we know that dx by dt because it is moving with the velocity v, so we will get b L v. So v EMF induced, so the magnitude of this EMF induced is BLV, and this is the polarity of the EMF induced using the Fleming's right hand rule, right? So this is basically a generating action. So this you can term as, so so um, hmm. So I'll give this slide the heading, sorry, generating action of a moving single coil moving conductor. Okay, because single coil, this is single conductor, right? Of a single moving conductor. Okay, so this is the generating action of a single moving conductor. So this is what as sir has discussed also. Now let us go to the motoring action. Okay, so this is motoring action in a single conductor. Okay, so now here what we are saying is that, let us say that, okay, you have these rails are like made of some conducting material. So if you connect some external wires through it and a battery through it, so what will happen is that it will form a closed circuit. So it will form a closed circuit like this. Okay, so it will form a closed circuit like this. So from this closed circuit, what will happen is the current will flow. Now, how will the current flow? We know that from the positive polarity of the battery, the current leaves, right? So current leaves the positive polarity. So current is leaving like this, and then the current is entering like this in the conductor. So how is the current entering in the conductor? So current is entering like this. So this is the current I. Now what we need to do is, so we have the, so first of all we have the magnetic field, same magnetic field from north to south. So it is going upwards like this, north to south. Okay. And then we have the current carrying conductor. So we know from our discussion from the in the first slide. So let us go to the first slide. So we know that if we have a current carrying conductor in placed in a magnetic field, then what it will experience force. Okay, and from the direction of force can be found using this Fleming's left hand rule. Okay, so now coming here, we can find the direction of this force using the Fleming's left hand rule. Okay, so what you will do is, so here you will place your left hand. So here you will place your forefinger in the upward direction. So this is the magnetic field B. Okay, then what about, so your forefinger will be like this. Okay, then what will happen? Your thumb will, so basically thumb will give us the direction of motion, but before that we have to place our middle finger in the direction of current. So if you will place it, you will place your middle finger something like this. Okay, and then this will be your thumb. So this is the thing, right? So here you have upwards force like this. You have the so you have north to south pole upwards, the your forefinger, your current carrying conductor basically. So you will have your hands in this position, right? Fleming's left hand rule. So what we have is, we have a current carrying conductor placed in magnetic field. Okay, so you will see that your thumb will point towards the direction of motion. So you will see that this current carrying conductor, so it is like this. So this is the direction of your flux. The current is moving away from you, right? So it is cross. So how it is experiencing the force? It is experiencing force in this direction. Okay. So what is the magnitude of this force? So we will see that the magnitude of this force is given by BIL. Okay. So how do we find this magnitude of force? So basically you will see that it is, this force is nothing but the, so force is given like this. Okay, you will see that in your electromagnetic theory course, you will see that the force experienced by a charge which is moving in the presence of magnetic field is given by this expression. Okay, so now what you will do is, you will rearrange this. Okay, so when you rearrange this, you will see that velocity is what? Velocity is dl by dt, right? Because this is the movement direction. Now this dq by dt will give you the current, and this becomes bil. But what you need to remember is, you need to remember this. Okay, force is equal to bil. Like here the emf, so important thing here is v emf is blv, and so this is the magnitude, and direction was obtained using Fleming's right hand rule. So here the important thing is that this expression force is equal to BIL, and direction of force, this is the magnitude of force, and the direction of force is given by Fleming's left hand rule. Okay, so these are the things. We will come back to this slide again. So now let us proceed. So these questions are very simple after all this discussion. Okay, you will find that these questions are very simple to solve. So let me discuss this also. Now you will see something. So let me um enter another slide here. Since we have some time, so I want to discuss some other things. Now I will discuss the um, Lenz's law in generator and motor. So it basically means what? This Lenz's law basically tells that there is a motoring action in generator also, and there is a generating action in motor also. Okay, we have seen the Lenz's law in the last class in the case of the transformer. Now we will see it in the motor and generator. Okay, so what I said that there is a north pole and south pole And let us take the case of generator first. Okay. Now, let us say this is one coil and it is rotating in this direction. Okay, so it is rotating in uh, this direction. So what we have is, so if we have to find the direction of the current, so you will see that, so we will find the direction of current using Fleming's right hand rule. So here what you will do is you will place your, again you will use your right hand rule. So if you use your right hand rule, you will see that for this, suppose for this coil. So what is happening is that this coil is rotating with its axis, horizontal axis. Okay. So basically what is happening is, so suppose this conductor is going up, this side is going up and this side is going down. Okay. So here the motion which is denoted by the thumb you in the Fleming's right hand rule is upwards direction, and this your forefinger, index finger, which denotes the magnetic field direction, is from the left to the right side. Okay, so when you do that, you will find that your middle finger is pointing into the plane. Okay, so this side is seeing the current induced as cross, and this side you will see, so this side is seeing the current as dot. Okay, so this is the generating action. So So this is the polarity. So generating action I have denoted by red colors. Now we will see the Lenz's law. Okay. Now what is happening? So what is happening is that this current, so now this is the situation. Okay. Now I'll use the other color. So we will see, so this is motoring action in generator. Okay. Lenz's law. So here again I am drawing the same picture. Now here you saw that this so you saw, what did you see? You see that you saw that, okay, so the current here is right now cross and the current right now here is dot. Now for finding out the, now because now what is happening, now this is a current carrying conductor in the magnetic field, so you will apply Fleming's left hand rule to find the opposing motion direction. Okay, so this is the opposing motion. So what you will do, you will place your forefinger from of the left hand from north to south pole, means from left to right. Then your middle finger is pointing into the plane cross. So you will see now that the opposing action will, for this cross side conductor, will give you the direction downwards, and this one will give you direction upwards. So you see earlier, because we were moving our generator using the prime mover like this, so here the movement was upwards and this was downwards. So because of this movement, because there is a movement of the conductor in the magnetic field, there was EMF induced. Now because there is an EMF induced in, because there is current carry, so because of the EMF induced, the conductor will carry some current. Now a current carrying conductor which is placed in this magnetic field will experience a force in the opposite direction. Okay, so this is the Lenz's law in generator. So that is basically gives us the motoring action in generator. Basically what is happening, there is a motion which is opposing the force, right? So that is how we generally things are done in this nature also, right? When we walk, we are opposing the friction, right? We are opposing the friction so that we can walk. We are, so when you find your movement, you will see that your movement is equal and opposite to the friction action. Similarly here also, there's this opposing torque. So basically your prime mover has to overcome this opposing torque so that it can generate EMF. Okay, that is what this motoring action or Lenz's law means. Okay, now coming to the motor. Similarly, in the motor also there is some generating action. Okay. So let me draw the motor. So for the motor, this is again the North Pole, South Pole. And let us say that here, let us take the opposite direction and let us see the our discussion in the opposite direction. Okay. So let us take that initially the motor was carrying. So initially motor is carrying current. So here initially motor nahi, basically conductor here. We are talking about only one coil. So initially the coil is carrying current and initially coil is moving in magnetic field. Initially this coil is carrying current in magnetic field. Okay. So here, so let me use. So what we saw that initially there was only movement on in the generator. Now because of this Fleming's right hand rule, we found that okay. So here the current is being carried like this, cross and dot. Now here what was happening was there is cross and dot already. So now what we are having for the motoring action in generator, we are having this cross and dot. Now this cross and dot is experiencing force like this in the opposite direction of the initial force. Initial force was upwards here. So initial force we found out here is downwards. Okay. So this is downward. This is upward. Okay. So this is opposing motion. Similarly, here also, I am saying that initially the coil is carrying conductor. So let us say the coil under conductor under north pole is carrying dot, and here it is carrying cross. So for motoring action, what we will do for for motoring action, we will use Fleming's left hand rule. Okay, so we will be using Fleming's left hand rule. So if you use Fleming's left hand rule in this case, so what will be the direction of motion? So let us see. So here the in the motor we will find the direction of motion using the Fleming's left hand rule. So your forefinger which is pointing the magnetic field is from north to south. Your middle finger is denoting dot. So you will see that the motoring action here, it will start, this conductor will start to move upward and this conductor will start to move downward. Okay. Now we will see the generating action in motor. So generating action in motor, Lenz's law. Okay. So here what we have is we have the movement, right? So we have the movement already. So we already have the movement like this. Now using the Fleming's right hand rule to find opposing EMF or back EMF. Okay. So you will see that if you use the Fleming's right hand rule, so you will see that here this is cross, this is dot. Okay, so you can use that. So you will see that this cross is opposing the dot here, initial direction, and this was cross, so this is dot. Okay, so this is how the opposing or generating action is coming in motor. Okay, so in this slide also sir has discussed the same thing. So I'll discuss what sir has discussed in this slide. Okay, so what was sir saying? So sir was initially saying that okay, there is a motoring action in this conductor. So what is happening is that this conductor is carrying conduct current. You can see that this is denoted by cross. So cross means current is carrying coming out of the plane. Okay, so you will point your middle finger of the left hand out of the plane, and this upward direction is the direction of your basically B. So cross means current in entering the plane. I said in the opposite way. So cross means current entering the plane, and B means it is going upward. So your forefinger of the left hand is pointing up like this. So your forefinger. So let me use some other color. So forefinger is like this. Okay, forefinger is like this, and your this cross means what? So your middle finger is entering the plane. Okay, so you will see that your this thumb is pointing like this. Okay, so these are your other fingers. Okay, so you will see that this thumb is pointing in this direction. So the force experienced is this direction, and we know that the force is given by BIL. We have seen that. Now what is happening? Now what we will see is that force is in this direction. Okay. And your B is in upwards direction. Okay. So if force is in this direction, B is in the upward direction. So you will see that from the right hand rule, the current will opposing current generating current will come out to be dot. Okay. So this is generating current in motor. Okay, so here because it was, so you will see that if you represent it, so because this was the battery due to which it was the current was initially flowing in this direction. However, this BLV, which is the opposing what you say EMF due to the generating current in motor which opposes the initial EMF, so this back EMF is opposing like this. So this positive polarity and positive polarity are opposing each other. Okay, so this is the BLV. So if you have to find the current in this case, so the overall current will come out to be, so this voltage has to be applied such that it will push the current by overcoming this BLV. So this current is basically V minus BLV by R. Okay, so this is what was sir discussing. So he was discussing basically Lenz's law only. Okay, now what we will see is we will see the questions are very simple. Once you have understood this whole discussion, questions are very simple to solve. Okay, so I will explain the questions one by one. So here what is given is, so here the same experimental setup is given which was shown earlier in this figure. Same setup. Okay, this is the same setup which is given here. So same setup is also given here. Now what is it is saying that the length of the conductor is 60 centimeter. Flux density, which is the flux moving from north to south pole upwards direction, north to south pole upward direction, is 1.1 Tesla, and the resistance is 0.25 ohm. Okay. Now they're saying that all other resistances are negligible, all frictional forces are negligible. The conductor is pushed, okay, with a constant force of 100 millinewton. Okay. Now, so what will happen? Because there is a conductor which is being pushed, right? So current which is moved in the presence of the magnetic field will have an EMF induced across it, right? So what will happen? Therefore, at steady state, the current conductor will have a constant EMF which will be induced. Okay. So now, so what we have to find is so basically what is happening? They're saying that you are using some force to push this current, okay, conductor. Okay. So that is why at steady state, this force which is used to push this conductor will be entirely, because it is there is this is system, there is no friction, no resistance, nothing. So what is happening is this force will be completely utilized to be transformed into EMF induced. Okay, this is what is being said in this question. So what is asked is, find the current which will flow through the resistance in the steady state. Okay, so there were two ways in which you could have done. If they would have given you velocity, then you would have known, okay, my EMF induced is BLV, and then current will be BLV by R. So this is one approach. But you will see that this velocity information is not given. Okay, velocity information is not given. So what you will do, so you have to understand that all the frictional forces are negligible, means whatever is the force being applied, that force is being totally used to generate to induce the EMF. Okay, so it basically means what? It basically means that this force into velocity is this EMF into I. So basically this is the input power and this is the output power. Okay. So it basically means what? It basically means that, so mm, I just wrote it like that, but you understand that what will happen is that this force will also be, so basically force is equal to BIL. Okay. So here I will be equal to force by BL. So what I mean to say is that this force is being totally utilized to generate this EMF, due to which this current will flow in the resistance. Okay. So that is why this I, which is generated by this BLV, should also be same as the force which is input applied, because there is no losses. So input power should be equal to output power, which I initially wrote here, right? So basically BIL into velocity should be equal to BLV, basically EMF into current. This is EMF into current, and this is force into velocity. So you can see that force into velocity is equal to EMF into current. Right, here also BLV into I, and here also V into BIL. So this you can see that BLVI. So this is applicable when there is no, basically no friction, no losses, as mentioned in the question. Okay, so no, all the other resistance are negligible, all frictional forces are negligible, then only this is applicable. Okay, so you can find the current using this EMF by R, or you can also find the current using this. So because our information to us was given for force and B and L, we will use this expression to find the value of current. Okay. So you will find current like how? Current is force 100 into millinewton divided by B 1.1 into L. L is, now you see, what you will do, you will convert everything into SI units. It is very important. So at SI unit or MKS unit is what? Basically, the SI unit of length is meter. Okay. SI unit of your flux density is Tesla. SI unit of force is Newton. Like this, so SI unit of current is ampere. Okay. So you have to convert everything into SI units when you are calculating. Then only you will be able to enter the correct what you say digit, uh, decimal points. Okay. So force by B into L. Now L is in meter. As I said, we have to enter SI units. Okay. So if you solve this, you will get in SI units 0.15 ampere. But they're asking in milliamperes, means you have to multiply by 10 power 3 milliamperes. So this will be 151 milliampere. Okay. So please convert everything into SI units when you're solving this kind of questions. Otherwise, you will not be able to enter your correct answers in proper decimal points. Okay. Then you will make mistakes in the decimal point which you are entering. So did you understand? So conventionally, what you should do is you should do EMF is equal to BLV by R. Okay. This is what you should do conventionally. So if the velocity information was given to you, then current would have been BLV by R. Motoring, basically by using the generator expression. Generator means current is given by EMF by R. But we are saying that okay, the input force which we are giving is being totally utilized for inducing the EMF. So that is because there is no friction or losses. So we can use this. So what will happen? We can, because there is no losses. So this current, if there were losses due to friction, then this current I, which would have been obtained by using this expression, would have been much higher than this expression. Okay. So in a practical system, I obtained from I is equal to F by BL will be higher than I is equal to BLV by R, as there will be losses. Okay. S- But because there are no losses, that is why only when there is no losses, then only you can use this approximation that okay, this current and that current which we are obtaining is exactly same. Okay, did you understand all this discussion? I hope you have understood. Okay. Now we will move to the next question. Now in the next question, we have to estimate the induced EMF. So how we will estimate the induced EMF? So we know that induced EMF would have been BLV. But velocity information is still not obtained to us. So what we will do is we will just do EMF is equal to I into R. Right? Because what is happening, this current is passing through this R, and this resistance is connected in parallel to this conductor. So whatever is the EMF induced in this conductor will be nothing but I into R. So this will be I into R. So this will be I into R. So it is like this. So you have a rail. It is connected in parallel. So this is parallel connection with this resistance, which is having the current I like this. Okay. So because it is having the current I like this, so will it have the current I like this, or it will have in the opposite direction? I think it will have in the opposite direction. Right, it will have in the opposite direction. Okay. So it will have current I like this. Okay. So this I into R will be equal to this EMF induced, because there is no losses, there is no loss in other losses, all resistances in the circuit are negligible. So what will happen is this EMF induced will be equal to I into R. Okay, so current you have obtained from this previous question. So here they're asking the EMF in millivolts, so you can keep the current in milliampere, and then milliampere into this resistance will give you the value of induced EMF in millivolts. Okay, so again, as here we have done some approximation that this current which is obtained by this F by BL is exactly equal to current by BLV by R. So here also we are doing the approximation that okay, here the approximation done was there is no friction forces, and here the approximation done was there is no resistance anywhere in the conductor. Okay, that is why this EMF induced is exactly equal to current into resistance. Okay, that is why it is given like this, that current in that there is all other resistances are negligible. This is the what you say approximation taken here. So here all the frictional forces are negligible. This was the approximation taken. So here all the resistances are negligible is the approximation taken for this question. Okay. Now we will go to the next question. Now in the next question, we have to obtain the steady state velocity in centimeter per second. Okay. First of all, you try to find your answer in meter per second. Okay. Then you convert into centimeter per second because it is easier to convert everything into SI unit. Okay. So what is the velocity? Velocity you know is induced EMF is equal to BLV. Now induced EMF we have obtained from this previous question. Right. So induced EMF is 37.87 into 10 power minus 3 volt. This is volt. Okay, don't confuse it with velocity. So I'm just erasing the units because you know the unit of voltage. Okay, is equal to BLV. So what is B? 1.1. Length is 60 centimeter means 0.6 meter into V. So V is 37.87 into 10 power minus 3, 1.1 into zero point 0.6 meter per second. Now what do you know? You know that 1 meter is equal to 100 centimeter, right? So 1 meter is 100 centimeter. So you can replace it because it is asking in centimeter per second. So you will just replace 1 meter as 100. So this will become 37.87 10 power minus 3 into 100 centimeter per second. Okay. So if you simplify this, you will get what? You will get, so let me just simplify this. You can also simplify and tell me. Okay. So let me simplify this. 37.87 to 10 power minus 3 into 100 by 1.1 divided by zero point 0.6. So it will come out to be 5.737 like that. Okay. So it came out to be 5.737 centimeter per second. Okay. This is also the similar kind of answer. So you first, my suggestion is instead of doing like this directly, you can convert everything into SI unit and then you can convert the things in whatever way you want. Okay. Then you will get the exact correct answer. Okay. And as per the concept wise, it was straightforward that EMF induced is equal to BLV. We know EMF induced from our previous question. We know B, we know L, we can find velocity. Okay. In these X questions, there was approximation done, but it is the same thing. So here we can do it directly. Now, here for this question, what we have to do? We have to estimate the power required to keep pushing the conductor at the steady state. So what will be the power? So we know power is equal to, as I said, force into velocity, okay, which is equal to V in this EMF into I. Okay, so let me write it as EMF into I instead of V into I. Then you will confuse if whether this is velocity or whether this is what. Okay, so I'm writing EMF into I. So how did this force into velocity is power? So I will say, so you know what work done is when you move, when you move something across some distance by using some force. So if you have some force into distance, so force into distance displacement is denoted by S. So force into displacement is work done. Now you know that d by dt of work done or d by dt of energy is power. Okay. So d by dt of force into displacement is power. So force into ds by dt is power, means force into velocity is power, right? So here you know the force, you know the velocity. So if you have to find the power, it will be force 100 milli Newton into velocity. Velocity we have obtained here. So this is 5.737 centimeter per second. 5.737 into centimeter per second. So that I'm converting it to meter per second. Okay. So like this much will be the power. Okay. And then another thing is, so this will be this and this will get cancelled. So this will be 5.737 milliwatt. Okay, in the what you say SI units of power. SI unit of power is watt. Okay, then you can find it also using this EMF into I. So what was the EMF? So EMF from this expression, EMF was 37.87. So this is, so power is equal to EMF into I also. And as I said, because there is no loss, so input power is equal to output power. So input power is basically BIL. Input power means this, which I wrote here, right? So input power is equal to output power. Okay, in this question. So that is why because input power is equal to output power, we can also write power here required for keeping this rail moving as BLV into I. Okay, BLV into I is also EMF into current, and because EMF we have already obtained, so EMF is 37.87 millivolt. So 37.87 millivolt into current. So current is what? Current was where? So current is 0.15 ampere. Okay. So 0.15 ampere. So this will also give you 5.737 milliwatt. Okay. Now we will move to the next set of questions. Now in this next set of questions, what is said is that here the length of the conductor is 60 centimeter, flux density is 0.8 Tesla, battery EMF is 0.16 volt here, and R is the 1 ohm. All other resistances are negligible, all frictional forces are negligible. How much electromagnetic force will act on the conductor at rest? So here basically what is happening is that here, so because again we are saying that here basically what we are assuming that all frictional forces are negligible. So it means that this input force, so force, because this is a current carrying conductor, so current carrying conductor will experience a force, right? Okay, we have seen that in the beginning of this class that current carrying conductor will experience force. Now what is the current? Current, in this current we will find it as, because all other resistances are negligible, so current will be directly E by R. So we know force, so force is B into I into L, because current, which is, so the suppose current conductor is carrying current I and it is placed in the magnetic field B, then it will experience force as B into I into L. Okay, so we know B is 0.8. Current due to this E and R will be 0.16 by 1 ohm. E is 0.16 volt and R is 1 ohm into L. L is 60 centimeter. So if you do this, you will get your answer in as 0.0768 Newton in SI units. Okay. Then you can convert it to other, like millinewton, they're asking millinewton, then 1, 2, 3, which will be 76.8 millinewton. Okay, like this. It was a very simple question. Just you have to understand the motoring action and generating action, and everything is easy, okay? Just have to understand the concept. Now, here they are saying that, okay, so what will be the direction of this force? So magnitude of force you have obtained. So what will be the direction of force which will act on the conductor? So we know that the direction of current carrying conductor can be obtained, current carrying conductor in magnetic field, in magnetic field can be obtained using Fleming's left hand rule. Okay. So how you will apply the left hand rule? We have applied exactly for the same problem. So here what is happening? So this is the rail. So current, so this is connected to this circuit like this. Okay. So current is leaving the positive terminal of the battery. So it is leaving here like this. It is entering the rail like this. Okay. So your current is like this. Your force, your basically magnetic field is like this. So you can find the force using the Fleming's left hand rule. So apply Fleming's left hand rule. So your index finger should point upwards. So your index finger is pointing upwards like this. Your middle finger is pointing in the direction of current. So it is like this. Okay. Then what will happen is your thumb will give you the direction of your motion. So you will see that because you have kept everything perpendicular, so this will be the direction of the motion. Okay, these are the other fingers which are down like this. Okay, so you will see that. So this is the direction of motion, thumb. This is the magnetic field direction, and this is the direction of current. Okay, so these are the things. So now you will see that your rail will experience force like this. So you are seeing left to right, right? This is from left to right. So left to right. So force will be left to right, okay, as seen by the reader. Now in the next problem, what it is saying is, if the conductor is allowed to move under the direction of the above electromagnetic force, and if there is no other force acting on the conductor, like friction, okay, then estimate the final steady state velocity. So how you will find the velocity? So basically, what will happen is that, so here, basically there is no opposing motion. So what will happen? That as I said that here, basically we have to find the velocity, right? So velocity is E is equal to BLV. And because there is, like what you say, there is no other force acting, there are no other resistances, and because this is like this, right? So here, so velocity is constant means, so you are, we are saying that we are not applying any external BIL. So there is no need for this. Okay. So basically what is happening is that, so when the velocity is constant, there is so there is no other force. So because there is no friction, so earlier it started moving with this BIL, so it will continue to move with this BIL. Okay, so what will happen is, in this steady state, this battery EMF will be equal to back EMF. Okay, so you can apply this approximation. So if you do this, you will get your velocity as E by BL. Okay, so you can calculate this. So E is 0.16 by 0.8. into 0.6. So if you do this, you will get 0.33 meter per second in SI units. And if you convert it into centimeter per second, so we know that 1 meter is equal to 100 centimeter. So 0.333 into 100 centimeter per second will give you 33.3 centimeter per second. Okay, like this. Now we move to the next problem. Now in this next problem, basically here what is happening is that here now we have attached this this pull this basically now we are applying some external force. Okay, so here we are saying that okay, earlier there was no external force, so in this question there was no external force, but now we are applying external force using this pulley. Okay, so this is the, so we are saying that okay, because of this weight, the force applied is 23.04 millinewton. Okay, so basically this external force external is 23.04 millinewton. Okay, this is the external force. Now, under the steady state, find the steady state velocity of the conductor. So we know that from this discussion, if we apply, so this Fe means you can say here as Fe is external force. Okay, so if you apply external force, if you, so this was the generating action, but if suppose you apply an external force here, so what will happen? This force and this will oppose. So here, so by using this slide, okay, so from this slide, I'm writing this. So here it will be battery EMF E minus BLV by R. This will be current. Okay. So battery EMF E is given as 0.16 minus we have to find BLV. Okay. So how we will find BL? So we have to find this BLV by R is equal to I. Now we know that this external force is equal to BIL. Okay. So this 23.04 millinewton is equal to B into I into L. So from this we will get I as 23.04 10 power minus 3 by B into L. So B is 0.8 into L is 0.6. So this will give you current. So this current will come out to be 0.048 ampere. Okay. So this is 0.048. So this BLV is 0.16 minus 0.048 because R is 1 ohm. Okay. So this will come out to be 0.112 volt. Now BLV is 0.112 volt means velocity is equal to 0.112 by B into L to 0.8 into 0.6. So this will give you 0.233 meter per second. They're asking in centimeter per second. You can convert it into centimeter per second. Okay. So that is what is happening. So you see under steady state here, because this external force, because we're not applying any external force, it is just moving in that way. So what is happening is that the current is zero. Okay. Because this you will see that uh, so because this external force is zero, so this external force is zero, which is BIL. So I is zero, and hence this induced EMF here will be back EMF here due to this movement will be same as this battery EMF. But here because the external force is applied, so back EMF and this battery EMF will not be same. Okay, so there will be some difference which will result in the current to flow. Okay. Now here it is asking the power supplied by the battery. So power supplied by battery is given by, so power supplied by battery, we know that the battery EMF is 0.16 into current, because this E into this I will be the power of battery. Okay. And I we have obtained from this previous question for this pulley system. So you will find it to be like this. What? Okay. So this is how you will find the power supplied by the battery. Now in the last question, what we have to see is what is the power utilized in lifting the load up? Okay. So what will be the powers which will be supplied for lifting this load up? Okay, so it will be equal to your so basically you can find it in two ways. Okay, one way is that because this power will be what? This power will be power supplied by the battery minus this I square R losses will be the power which will be required, because this force equal to BIL should match this external force, right? So this force, so this so power, so this so first of all what we will do is you can also do it like this, that power is equal to BIL into velocity. Okay, so this is how you can do. And the other way you can do is power is equal to this battery power minus the heat loss. Okay, this way also you can do. So you can solve it in the both the ways. Okay, now we will discuss some other things. Now here we will discuss some generalized things, though these are the part of the assignment 3, but I'm discussing this right now because sometimes some questions may be there in the present assignment for this assignment 3. So I'll be discussing some of the generalized terminologies. Okay, so so here if you see, so this is as I have drawn earlier also in this slide, you will see, right? I was placing one coil. So you can see I was placing one coil. So you will see that this is one coil. Okay, so this is a single turn coil. This is having only single turn. But if you have, so in the single turn coil, there are how many conductors? There are two conductors. Okay, so there will be two conductors like this in a single turn coil. Okay, so in a single turn coil, there are two conductors. So let me just write it in a fresh way. First of all, what is a coil? A coil is something like this. So single turn coil. So single turn coil is like this. Oh, single turn coil consists of, okay, क्या हो गया? Consists of two conductors. So these are the two conductors. Okay, so these are the two conductors. Now, what is a multi-turn coil? So this will be having multiple turns like this. So here you can say that this what I have drawn is a two-turn coil, because how many turns are there? There are two turns. Okay. Now what is a coil span? Okay. So you will see that coil span is nothing but in a coil there are two conductors. Right. Now, when you are placing them in the slots, so what are the slots? So, in the stator, you have something like this. So, in the stator, you have poles like this. Suppose, let us talk about DC machine. If we talk about DC machine, so these are the Stator poles. Then the rotor, you will have something like this. You will have slots, okay, to place these coils. The coils which I'm drawing right now. Coils which I've drawn right now. What I'm drawing is the slots, okay? So this is the rotor. So these are the slots. Now in these slots, there will be some holes, okay, like this, in which you will place your coils. So you will place your coils like this, okay? So suppose it's a coil. So you will place your coil something like this. So it is starting here. So these are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So if it were like 8, then it would be good. So let us say it is having 8. Okay. So let us say, okay, it is having 8. Okay. So let us say it is having 8. So there are suppose 8 slots, okay, in a machine. And we have drawn 4 poles. 4 poles. Then how many slots per pole? Very simple, total number of slots by total number of poles. So for this example, you will see this comes out to be 2 slots per pole. Okay, 2 slots per pole. Now here what will happen is if I have to place this coil now, so if I have to place this coil, so I will start here, then because there are 2 slots only, so this 1 slot and 2 slot, it is over in the North Pole, then I will place it here. Okay, this is how I will place. So you will see that one coil is under, conductor of this coil is under North Pole and the other conductor is under South Pole. Okay, this is how it generally is. So you will see that this is equivalent. This is called as coil span. Okay, distance between the two conductors or distance between the two consecutive north and south pole. This is called as coil span. Now, in in electrical degrees, this coil span is equal to 180 degree electrical. Okay, so this is 180 degree electrical. But you see, if you see like this is also 180 degree electrical. This is also 180 degree electrical. And this is also 180 degree electrical. Okay, you see there are how many? 360 plus 360, 720 degrees electrical total. But mechanical degrees are 360 degrees, right? So what is the relation between the mechanical degrees and electrical degrees? So mechanical degrees equal to P by 2 into electrical degree, where P is the total number of poles. Okay. So this is how you will find, this is the thing between this is the relation between mechanical degrees and electrical degrees. So in this diagram, 180 degree electrical means 90 degree mechanical. Okay, in this diagram. which we can see here also, right? That you can see that from here to here, this is 90 degree, right? So this is 90 degree mechanical. Okay, for this example, like this. Now, what all things are discussed to remain? So let me keep this. Okay. So this is the same things which I have just said. Okay. This is the same things which I have shown earlier. So I'm writing the same things here also. Okay. So I'm deleting this because I discussed this. Okay. Now, um, so this is an example of the what you say. So as I said, single turn coil has only one turn. Multi-turn coil has multiple turns, which we have seen, right? Multi-turn coil has two-turn coil. Okay, two turns. A coil span is 180 degree, and this is the relation between electrical degree and mechanical degree. So this is equal to total number of slots per pole, which will give you the number of slots per pole, and this that will be equal to number of slots per coil span also. Okay, now this is a single layer winding in which you have only one slot, but in so you have only so you have capacity to hold one end of the coil in this one slot, but here you can hold two end of the coils in one slot. That is double layer winding. So you will see that for double layer winding, you can see that the number of coils will be equal to number of slots, whereas for single layer winding the number of coils will be equal to number of slots by 2. I've discussed these things so that you will know what all these double layer winding, single layer winding means. Okay, so you can refer to this slide. Now, maybe we will discuss these things in the later class. Why? Because these are some different kind of concepts. So, because I have already discussed too many things, then it will be like too much along with the questions. So I think that is it for today's class. So I'll start with discussing these things in the next class. Okay. So, so that is it. So I'll stop the class here. Okay, for today. So let me stop.